All right, modeling data with quadratic functions. This one's going to be very short. This is mostly just throwing everything into Desmos and doing regressions. Okay. So we're going to take this. Tamara's hitting baseballs during batting practice. Following table displays the vertical distance. Just so we know, vertical is up and down. Above the ground, the ball is of one particular ball hit is corresponding distance from home plate, both measured in feet. So horizontal distance, vertical distance, just to remind us. So we're inputting this. Determine the data to be most appropriately modeled by a linear, quadratic, or exponential function. Explain your reasoning. Usually quadratic involves, going up and down. So that's going to, tell us here. But we can put all this data in here. So we're going to insert a table. And we've got 0, 5, 10, 20, 50. We've got 4, 10.42, 16.68, 28.72, and 61. Okay, we can plot it, we can look at it. There looks fairly straight. That's one of the things that's you're going to think it's pretty linear. So we hit that. Linear regression gives us an R squared that's pretty darn high. That's pretty good. Let's check what else we got. We can check the exponentials. The other one we did, our R squared went down just a bit. So, and obviously you can look at that and think, when you're obviously thinking exponentially, is the ball is not going to keep going up. Probably tells you a little more too. So let's try a quadratic. Hey, look at that. Our R squared is 1. So here is our function that we're going to need. Writing it down so I make sure it is 0.0032 x squared plus 1.3x plus 4. Okay. So back to here. So it's quadratic mainly because ball goes up, then down, like a parabola. Also, R squared was 1. The closer to 1 with R squared, the better we got. So we got a function of y equals 0.0032 x squared plus 1.3x plus 4. Height of the ball when it's 100 feet away from home plate, well, you're just putting in 100. We do negative 0.0032 times 100 squared plus 1.3 times 100 plus 4, and we should get around 102 feet. All right, pretty simple. Let's check another one. We don't need that. Delvin is practicing free throw shots. After a jump, Delvin releases the basketball from a height of 8 feet above the ground. So when the ball is 0 feet away from him, when the ball is right here, and this is 0 feet left and right, our y, our horizontal distance, is 8 feet. Now, when the ball is 2 feet more this way, so 2 feet horizontally, the ball is now 11 feet. So we'll put that in. And then when it's 15 feet, goes through the basket, which is 10 feet above the ground. So we're just taking this to Desmos again. And let's get rid of that, insert our table, and now we're talking 0 to 15 8, 11, 10. Zoom in on it. That's a weird looking one. So let's add a regression. Linear is obviously terrible. Exponential is going to be terrible. We got a 0.09 instead of 0.99. And hey, when we do a quadratic, hey, look, that r squared equals 1. Very rarely in the real world will r squared equal 1. So we are talking about, there's our function, negative 0.10528x squared plus 1.71026x plus 8. So there's our function. Y equals negative 0.10528x squared plus 1.71026, lots of numbers, plus the 8 feet we start from the ground. Now, it wants to know what's the maximum height. And all you do with that is zoom out. I wonder if this will let us, no, just zooms to data. We're looking for the maximum height. So when the ball is about 8 feet horizontally, we get about 15 feet maximum height, because this is the horizontal distance, this is the vertical distance. So you just find the maximum of it, and that's your answer. So what's the maximum height? Max height is about 15 feet. And there you go. That's what quadratics are used for. Good luck.